Measures of variability. Let's kick this up a notch. So I title it this because measures of central tendency, once you kind of get the routine, once you get the process of calculating them, it's pretty easy and straightforward. Measures of variability get a teensy bit more complicated. So this time we're not looking at how is our data similar, how do our numbers sort of tend to centralize around one another. This time we're looking at how do they vary from one another? How are they different from one another? Like this image right above me. How do they deviate from one another? Of course, we need both to fully understand what's happening in any kind of data set that we're trying to figure out some sort of meaning from, that we're trying to draw meaning from. So we're going to focus on variability here. I do want to do a quick recap of mean, median, and mode. Like the previous video, I will invite you to pause the video and see if you can do these calculations on your own prior to me running through them. We're going to calculate central tendency for these statistics here you see in front of you, and then we're going to practice our measures of variability. So in this example, I have a lovely image to demonstrate exactly what it's like to find parking on campus at the University of Nebraska, Omaha. So maybe you can relate to that. I almost chose one with just like busy cars in a parking lot, but I thought this was funnier. Like, how does that happen? I don't know. Poor car, poor person who owns that car. So it could always be worse is my secret message to you in this slide with parking. Though sometimes it's hard to feel that way. So we are using minutes spent looking for parking as a very relevant example for a lot of us who are trying to attend college and struggling to find parking. So I asked 7 students, how long did it take you to find parking today? Hypothetically, in reality, I made this up. So I hypothetically asked 7 students, how long did it take you to find parking today? One student took 10 minutes, several took 30 minutes, 20 minutes, one poor student, student number 4 had to look for parking for 40 minutes before finding a spot. So here is your invitation. Pause the video now, See if you can run through these calculations so that you can compare your answers to mine. Okie dokie. Here is our equation for mean. We've got sigma of x divided by n, meaning add up all the numbers in our data set, divide them by the total number of people represented in our data set. Here are all those statistics now. We add those numbers up. Hopefully you get the same thing I did, which is 180. Take 180, divide it by 7, and you get roughly 25.71. I always err on the side of just summarizing to 2 of those decimal places. Anything beyond that gets a little cumbersome. At the PhD level, maybe we need to know that level of detail. At this level, we don't. Just round it, that's fine. We end up with an average waiting time of 25 minutes, 71 seconds, I guess. That doesn't really mean much anyways, right? Median, if I stack all those numbers out and find that middle point, I get 30. Hopefully that's what you got as well. Mode, if I look at what is the number most represented in this data set, 30 is represented 3 times. 3 students had to wait half an hour. The mode is 30 minutes, same as the median. Okay, so we're going to get into calculating those measures of variability, but I first want to point out, why does this matter? Why do we need to know measures of variability in order to do statistics, in order to understand statistics? So here's an example. We did these calculations just a second ago on the previous slide. We calculated that the average time spent looking for parking in this class of 7 students that I asked, how long did you spend looking for parking? The average was 25 minutes and 0.71, whatever that means in terms of 0.71 of an hour or 0.71 of a minute. So I would invite you, if you're up for the challenge, calculate the average of this second class I've got over here. So same steps that we just did, calculate that average out. So pause the video if you need to, because I'm going to show you my answer. Surprise, it's the same answer. So you probably got the same average. Hopefully you got the same average. However, when we look at these scores, when we look at the difference between the amount of time that people had to wait, we can see those scores are vastly different. We can see in my first class, people waited anywhere from 10 minutes to 40 minutes. In my second class, everybody had a pretty good time of it. Most students had to wait 10 minutes. One poor student, again, student number 4, that poor student number 4. Student number 4 had to wait 100 minutes. What torture. So you can see, even though we've got the same average for both of these data sets, the numbers represented here are vastly different. So here's a real-world example. Here's a real-world illustration of why measures of variability are important, because very often they tell us something about our data set that the measures of central tendency are not going to tell us. How could this be? We're going to take a look. All right, so we're going to visualize this. Again, get a piece of paper if you have not already done so. We're going to map out how this plays out, and then we're going to talk a little bit more about those measures of variability, what they mean, etc. So I'd invite you to fold a piece of paper in half, sort of like this up here in the corner now. On one half, you're going to ultimately, not right now, but on one half of the paper, you're going to focus on class number 1. On the other half of the paper, you're going to focus on class number 2. So fold your piece of paper in half and draw 2 lines like those blue lines up there in the corner. So those blue lines are going to visually represent the mean, which was the same for both of these classes. The mean is 25 minutes roughly, 26 minutes roughly. And then I would like you to plot each of the scores between these 2 classes. So in your first class, you'll add an X somewhere on your paper. This doesn't have to be a perfect science, but add an X somewhere on your paper that seems to signify, like, roughly here's where 10 minutes would be as compared to the line, the mean of 26 minutes. So you'll add your 10 minutes, so then your 30 minutes is going to go above that, etc. So it's helpful to visualize this for yourself. So see if you can map that out on the piece of paper. And then the same thing with the second class side. So you'll end up with something that looks like this. So now what does this tell you about the average? What does this tell you about the mean? What conclusions do you draw from this? It's very possible for us to have vastly different responses to whatever kind of survey, whatever information we're trying to gather. It's very possible for us to have vastly different responses between 2 different groups, and for those groups to still end up on the same average. So that's what we're seeing here. If it wasn't already clear to you, hopefully now this sort of visual illustration has helped it make sense. Even though these numbers are vastly different, we're still ending up with that same average. Hence, why measures of variability are important as well. So we're going to return to this illustration when we talk about standard deviation in particular. I'm going to actually break up this video and have a separate video that's going a little bit more in depth into standard deviation. We'll return to this example, we'll return to this illustration, because it can also help us understand how is standard deviation, which is a slightly more tricky calculation, how is that reflecting the sort of difference in responses? What does the standard deviation mean? If we calculate something has a standard deviation of 2 versus 5, what does that actually mean? What is that telling us? All right, so measures of variability, as we have talked about, are valuable and helpful because very often we end up with an example like we did on the previous screen, very different set of numbers, same or very similar measures of central tendency, especially that average can end up being the same even though the numbers are vastly different. So we have 2 main indicators I'm going to talk about here. We have range. So range is an easy one. Range is looking at the range between the highest score and the lowest score. So essentially the range is looking at like how much space is there in between that highest score and that lowest score. So if we have a higher number for our range, that means that there's more distance between them. If we have a lower number for our range, that means that there's less of a distance between that highest value and that lowest value. So for this calculation, we use two scores in the distribution. We look at the high score, we subtract the low score from that high score. If we were doing these calculations for these two classes, this example we were just looking at, we would take, for this first class, we would identify the highest number, which is 40. We would look at the lowest number, which is 10, and we would subtract 40 from 10. We would get a range of 30. So that tells us that there's 30 minutes, essentially. 30 is the range between the highest and the lowest score. So if I'm looking at my data set, they're sort of close, within 30 minutes of one another from the highest to the lowest. Now see if you can calculate what is the range for this next score. For the second class, what is the range? $100 is our high score, obviously. 10 is our lowest score here. We subtract 100 from 10, we get a range of 90. So already we're seeing that if we were to only share the average and tell people like, hey, I did this study, I looked at these two classes, the average time students are waiting for parking is 25 minutes, 26 minutes roughly. That's only a part of the story. If I were to also then share, did this study, looked at these two classes, they both had an average wait of 26 minutes. However, the range of one class was 30 minutes and the range in the other class was 90. Then I'm getting a sense that that second class, there's quite a bit more variation, right? Like there's quite a bit more distance between the highest and the lowest score there, meaning that there's a lot of stuff going on in between. They weren't quite all congregated the same way that the first class was. All right, standard deviation. So this one tells us, I would say standard deviation is sort of comparable to the average, sort of comparable to mean, because this one tells us how on average, how much do responses differ from the mean. This is a calculation that uses every single score though. So it's taking a look at every single score in our data set, mapping it out sort of similar to how we did on that piece of paper a couple of slides ago. If this line is representing our average, and there are scores that are above our average, and there are scores that are below our average, the standard deviation is taking a look at the distance between each score and that average. So distance from this bottom score to the top score, or the bottom score to the average, difference from the score on top to the average. It's taking a look at all of those differences, and it's taking an average of those differences. So we're going to practice calculating this a couple times, and then I mentioned in the next PowerPoint that I'll do, the next video that I'll do, I'll have a more detailed illustration of how this actually looks, so you can visualize what it is that we're seeing, what it is that we're doing when we're calculating standard deviation. So it is a bit more complicated to calculate. Similar to the range though, a higher standard deviation tells us that there's more variation between our scores. There's more kind of uncertainty happening within our scores. They're not quite as similar as they were in that first class who only had like 30 minutes difference between the person who waited the least amount of time and the person who waited the most amount of time. So this is a lovely formula for standard deviation. Don't let it scare you. We're going to walk through it one step at a time. The good news is that we are already familiar with all of these statistics. So we're already familiar with these symbols. We just have to figure out now, how do we plug these in? So I will do a quick recap of the symbols in case you missed it in the last video. The S, as you might imagine, stands for standard deviation. So when we see S equals this massive equation, the S stands for the standard deviation. This is how we are calculating the standard deviation. We will end up, after we plug in all our numbers, we will end up with the S value. That's what we're figuring out. We're sort of detectives, if you will, trying to figure this out. The sigma sign means, as you may recall, summation. sigma sign is a command. It's not something we're plugging a number into. We're not plugging a number into sigma like we are for the other symbols we have here. Instead, it's telling us to do something. It's giving us an order. It's telling us, add all this together. So the X, big X, represents each individual score in our data set. We'll walk that out a little bit. X bar, as you may recall, means the average, the mean of all the scores. We do have to calculate mean in order to calculate standard deviation. That's the tricky thing about statistics. Very often we're calculating something so we can calculate something else. And n is size of the sample. A little n is size of the sample. The big N means something else that we'll get to eventually. So, mentioned variance previously. Range, standard deviation, and variance are the three measures of variation. However, we're not going to talk about variance right now because variance is really only useful when it's used in calculation with something else. It is very rarely used as sort of an individual calculation on its own. It's essentially S squared. So it's once you figure out the standard deviation, if you square that, you get the variance. However, in translation, like that doesn't really necessarily mean anything. It doesn't help us understand a particular data set better. It's primarily used in more inferential focused statistics where we're trying to add on some more complicated statistical formulas. So we will get there, but not today. Okay, so we're going to try this with a couple smaller examples. So I have this previous example from the video on central tendency. We already calculated the mean, median, and mode, so you're welcome to try those out, practice those if you'd like. I'm not going to walk through those equations again. I'm just going to throw the numbers up there though, so if you want to try it yourself, take a pause now, pause the video. There are the answers. However, let's practice calculating the range and the standard deviation. So, take a look at this, remember what the formula is for range, see if you can figure out what is the range here. The range is the high score minus the low score. It's easy when we only have 5 people. The range is 7 candy bars. Now, standard deviation. Here is our lovely equation. We're going to walk this out slowly together. Okay, so we know that the sigma sign, that little E, the Greek looking E thing, the sigma sign is telling us add all these together. We know that the X represents the individual value in our data set. X bar represents the mean. What this is telling us to do is to, over and over and over again, for each individual score we have, it's telling us to take that individual score, so here are my parentheses, so this is what that means, this is a parentheses. So it means take that individual score, subtract it from the average, square it, and then add all of those values. How it starts to look. Let me tell you what I've got here. So the X is each individual score. So for the 5 numbers I've got in my data set, I have something in parentheses for each of them. So there's person number 1's score of 3 candy bars. Here's person number 2 who ate 3 candy bars. Here's person number 4 who ate 1 candy bar. Person number 3 who ate 1 candy bar. Person number 4 who ate 5 candy bars. And the last person who ate 8 candy bars. So I've got that represented. For the 5 people I have, I've got 5 sets of parentheses. I'm going to have to calculate those numbers 5 different times before I can do the command of adding them all up. So for each of these values, I've got the individual score in my data set, the person's response, and I'm subtracting it by the mean. So the mean is 4. We've calculated that. Ta-da. So I've got 3 minus 4, minus 4, minus 4, minus 4, minus 4. And then each of those is going to have to be squared, which we'll do in a second. Then on the bottom in this equation, I've got n minus 1. So we're going to take the total number of people in our set, in our data set, which is 5 in this situation, and subtract it from 1. So right now I'm just going to plug 5 minus 1. My biggest advice, again, unless you are someone for whom this comes very easily, my biggest advice is to map this out in steps. I realize it's a little bit more tedious that way. I realize it's a bit more cumbersome that way, but it will help you practice. And more than that, it will help you stay clear on what step are you in. This stuff is really like it is sort of like detective work, and you have to take things a step at a time. So if you map out all the steps and you give yourself the time and space to do that, you practice some patience with yourself, recognizing that these are numbers and numbers can feel overwhelming just to look at. If you allow yourself that space, it will be a much easier process. It will be a much more straightforward process. So I'll do that in each of these examples. I would encourage you to do that on your end as well. So the first thing that we want to do, again, this is a lot of numbers that we're looking at here. So we want to start slow. We're going to take some small steps and we're going to map this out one step at a time. So the first thing we want to do is just condense what's in those parentheses. So we want to start with the stuff in parentheses. Let's condense that down so we know what number we're supposed to be squaring in each of these different situations. So when I am to do that, 3 minus 4 is -1. 3 minus 4 is -1. 1 minus 4 is -3. 5 minus 4 is 1. 8 minus 4 is 4. And you can leave those in parentheses too. I took the parentheses out around the 1 and the 4. But if it helps your brain, if that makes sense for you, leave that in parentheses too. So we've taken one step with our math. We have simplified what's in parentheses. We are also going ahead and subtracting 5 from 1 on the bottom. Get that math out of the way too. And now we have to square these numbers. So as you may or may not recall, this little tiny 2 up here, it's asking you to square that amount. So it's asking you to square that number. What squaring something means is we take that number times itself. So tricky thing about standard deviation, sometimes we do end up with negative numbers. However, what happens when you take a negative number times a negative number? Do you know? Let's pull up a calculator. So if I had -1 times -1, it turns into a +1. So the same thing would be true if I had a number that was not a 1. So let's say I had -2, so there's -2, times -2. It turns it into a positive number, it turns it into the number 4. So when we square these numbers, the negative sign goes away. We take the number times itself. Use a calculator if you're not comfortable doing that in your brain. And sometimes it's really hard, like squaring a number like 17. What's 17 times 17? I don't know. 1 times 1 is a little easier. 2 times 2 is doable. But just use a calculator if you're more comfortable that way. You can do the actual number times itself. Like, let's take the 4, for example. So I can do 4 times 4 to square 4, find out that it's 16. Your calculator likely also has, however, if you hit the number 4, it likely also has a way of squaring that number already. So your calculator on your phone might, I'm not sure totally about that, but here, if I just hit that button, it tells me that 4 squared is 16. So that's our next step. So here it is simplified. Now I have narrowed this down to here's -1 squared, -1 squared, -3 squared turned into 9, 1 squared also turned into 1, 4 squared turned into 16. And now I'm just going to add all of those numbers up. So now we're going to go ahead and do the command of the sigma sign, which said, do all this stuff and then add it up. So now we're going to add it up. And when we add those numbers, hopefully you get what I get, which is 28. So now we've got 28 divided by 4, still within that tricky square root sign. So we're going to go ahead and take the extra step. We're going to divide 28 by 4, so we end up with just one simple number there, and we're going to take the square root of that. So 28 divided by 4 gives us 7. Now the square root is not something I would advise trying to calculate in your head, again, unless math is something that comes very easy to you. I would instead recommend using a calculator. That is totally okay. So in this example, in this calculator on my laptop, all I have to do is hit this little square root sign, and it will tell me my answer is 2.6457513110, etc. Again, we're going to round in this process. So we're going to round to, I would not go more than 2 decimal points. So we're going to round to 2 decimal points. So how would I round this into 2 decimal points? See if you know that already. So I'm not going to just say 2.64. When we're rounding a number, we have to look at the number that comes next. If the number that comes next after the point we're cutting it off, if that number is 5 or higher, then we have to make the number just before the cutoff point, that second decimal place there, we're going to have to make that number 1 number higher. So this would be rounded up to 2.65. Done. Easy. 2.65 is our standard deviation. Huzzah! Okay, let's try that one more time. Oh, this time I threw the mean, median, and mode up there for you already. This is also a previous example we've already done. But let's try that out one more time, get our practice in. So what would the range be here? Our range is 6 minus 0, which is 6. Nice. So range is going to be 6. Now, how about that tricky standard deviation? Let's walk through this again. So here's our equation. So now I would invite you, pause the video, hit pause, get out your pen and paper, see if you can map this out for yourself. So take a minute. Okay, so if you are ready, here are all those numbers plugged in. So compare this with your notes, see if you put things in the same place I put things. Here's all of our numbers bumped down. Now hopefully you've also taken the next step. If you haven't, hit pause again, see if you can get all the way to the standard deviation calculation. And I will show you my answers. So here is after I have subtracted all that stuff in the parentheses. Here's the stuff that I'm squaring. There my results are of the squaring process. Now I just got to follow the directions of sigma, add it all up. I end up with 24 divided by 4. When I take 24 divided by 4, I get 6. And when I take the square root of 6, I end up with this big calculation. So hopefully you have also rounded your answer up to 2.45. The standard deviation here, 2.45. All right, that is enough practice of the mechanics of standard deviation. Tune back into the next video to get a little bit better picture of what do those numbers mean? When I'm looking at a standard deviation of 2.45, what is that even telling me other than just a random number? So tune back in to the next one.